In this video, I'm going to show you how you can use QuPath to do a nuclei segmentation with Stardist. So Stardist is a deep learning approach to instance segmentation, which is individual identification of objects. But for complex objects, and it's mainly used for nuclei segmentation, it's probably the most used deep learning approach to segment nuclei in microscopic images. So to do so, you need to first install the Stardist extension for QuPath. So let's go on the internet. If I type in QuPath, nothing there, QuPath Stardist extension, then you can go, so it's on the GitHub, so that's probably this one. QuPath extension Stardist. So you can scroll down, go in the releases here. You can directly go to the releases here. And you need to download the jar file. And then you can just open, so it's going to be in my download folder. And you can just, I already downloaded it for previous installation. You can just drag and drop, and I guess it was already installed, but you can check if it's installed. If you go to extension, installed extension, you're gonna see if, yeah, so Stardist is installed there, Stardist extension. And then to call Stardist, you need to open a script. So I'm gonna go back to the folder we downloaded from GitHub, which is this one. So in the script, you have two scripts and a model. So it's a model that I trained, so a Stardist model that I trained with data from TissueNet paper. So that's a paper from the Van Valen group in Caltech, where they they provide a ton of annotations for nuclei and membranes. Microscopic data, so that's really useful to train a model. They also introduce another model, which is Mesmer. But here I used their data to train the Stardist model. I also used two other papers I wrote, where we had polyp data that was annotated and intestinal epithelium of mice that was annotated. I put all these data sets together to train a Stardist model. To obtain this thing, this model, and these are the scripts. So what we're gonna do, we're gonna copy this folder script directly in the project, in the QuPath project, because I wrote it so that it's gonna call the model that is in the script folder in the project. So if you created your folder anywhere, it's going to be able to find it. Otherwise, you can just change it. I'm going to show you how you can do it. Now I'm going to open a script, so I can do Control-L and then script editor. So show script editor. I'm going to open the one that is nucleus detection and hematoxylin DAB. So if we have a look, there's so first thing is, where is the model? It's there. So that's the model I just showed you. And just briefly speaking, here we extract path input, which is where the project is, and we just add script and the name of the model. So if you were to change the model, so the model location, you would have to change that. You could also put your model in one location and always put the same location. Just to make sure that you have the model. If you just did the way I did it, copied it there, it's going to work. The only caveat there is that you're going to have to always copy a folder with script and the model in it. But that will work. So that's the easy way. So then we have several parameters. So this line corresponds to normalization. That's normalization I used when I trained the model, so you shouldn't change it. This is a pixel size, so that's pretty smart because it allows you to change the scale of the nuclei that are that are segmented. So if you were to look at nuclei that are smaller, it could still work if you change the scale here. So if you decrease the scale, you're going to get smaller nuclei. If you increase the scale, you're going to get larger nuclei. That's really nice because one thing that doesn't work well with deep learning is that you can find strategies of the people who worked on this, but most of the time it's going to be defined for a certain range of size. And so if you change the scale of the object you're looking for, it's not going to work, except if you change somehow the scale of your images. So that's really a nice feature. So here we do the stain deconvolution to be able to segment in both channels. I'm going to show you if we do just one, so if we do just the hematoxylin, just the dab, and if we do both. Cell expansion is the same thing that with the positive cell detection, the watershed-based approach. It's just to see how we expand the cells, and there's a constraint on this, the way the cells are expanded. Measure shape, measure intensity is to add measurements for both shape and intensity for nuclei, cells, cytoplasm. And here, in this thing here, is just to show that we take the image, we then consider the selected object. So we're going to need to select the annotation we want to segment the nuclei in. If we want to do it in several annotations, if we select all the annotation, that will work. And then we just run Stardist. So main parameters for us will be the pixel size, the threshold. I forgot about this threshold, really important. Stardist gives an output where we have the probability for nuclei to exist. So if you increase the threshold, you can have less nuclei. And I also added this and this, which is just to have the possibility to filter out the nuclei that are smaller. So here, all the nuclei that have an area smaller than 15 micrometer squares will be filtered out. When it's done, it stays down. So what I'm going to do is just define a small annotation because it takes a little bit of time. So let's say, like before here, we have both DAB and hematoxylin, and with elongated shapes and other shapes. And I'm gonna just show you, what's the importance of the stain deconvolution. So here, if I put this in comment, if I comment this and I comment the comma, so here I only consider the first output of the deconvolution is going to be the hematoxylin. So this is what I get. So it takes, a little bit of time, maybe a little bit more than, not maybe, a little bit more than with the watershed-based approach. So maybe I could define a smaller area, but that's still, pretty fast. So here is what we get. So I'm gonna just show as before the nuclei only. So here two things. We don't have the small ones, and we are missing some DAB, clear DAB. So there are some DAB we get, but we are missing others. So if I change this and I put it 2 instead of 1, now I'm just considering the DAB. And so I'm going to miss a lot of hematoxylin, but I'm going to get all the DAB. So when it's down, it stays down. Yeah, so now it's down. And here it's clear. You see now we don't, when it's just hematoxylin, we don't extract the nuclei. But when it's DAB, we get them. And so here the threshold wouldn't be suited because we have these kind of things that do not correspond to nuclei. But one way to work around is to, so either you use models that are trained with HDAB and you use the 3 channels RGB and you apply them. The thing is that you're going to need a model for HDAB, you're going to need a model for HNE, you're going to need a model for every single staining you're going to make. So that's not very convenient. So here I just train on fluorescence images, and if I do it right, you see I can segment the DAB, I can segment the hematoxylin. So one way would be to do it both and then combine the nuclei, because there are nuclei that I'm going to segment in both channels, or I can do this small trick where I just combine them. So it's something like adding both of them. So when I do that, I have some warnings, but it's fine. The warnings are because of that, because I'm trying to put two channels together, but it's okay. It's still going to work. It's going to take a little bit more time, even because I do this, but it's almost the same. You know, the great thing now is that I can segment both of them. I have all the DAB, I'm missing the DAB, especially when we don't have. So let's, if we just look at the DAB, just look at the hematoxylin. You know, for example, this is very faint in hematoxylin, and I think if I look at the DAB, that's very strong in DAB. So I would have missed it if only the hematoxylin, and now I have it. Next question is this, guys. Are they nuclei? And so are they nuclei of interest, at least? And so that's one question which is important, because if they are, I need to decrease my threshold. So let's say sort of 25. And I might get them, but I don't think that's the main problem. Main problem might be because of the area. And so if I want to get them, I might have to decrease the threshold of the area. So now it's down, I still don't have them. So one thing that might be useful is to select, you know, small ones, like, you know, this one looks really small. And what's the area? The area is 16. So if I put a threshold at 15, you know, that's almost the smallest area I can segment. And at the same time, now I have this kind of things, which is really nothing. So I need to increase my threshold for sure. And let's see if I don't filter out any of my nuclei. What? Oh, so here I need, the only thing that is selected is this nuclei. So I need to select again the annotation. Now it's good. And I can run it again. And now it's going to work. Yes. So let's just wait for the down. And then we'll see. So you see now we get these very small nuclei. Not these ones. Maybe too small. But this one, get it. Area is 3. 3 is probably too small. This is an area of 10, so maybe I can go down to 10. That's going to be better. Other than that, you can see that, you know, the Stardist approach is extremely powerful. We never have any shape that wouldn't make sense, and it's because we only extract convex shape. When we have nuclei that are touching, it does quite a good job. Now, when we have very elongated cells, it might be a problem, and mainly because I don't think that in my training data set I had that elongated shapes, which is really basically just a rod. We can see when we have these kind of things, it's able to segment it, but not as a long elongated shape, but more something a little bit larger. You see? So probably this I won't be able to obtain them with the model I have because of the data I use for training. I'm just gonna increase this to 10, so I'm gonna just get rid of the small ones. Overall, you know, it's not perfect, but it's quite nice because when you look, oh, I forgot to select it again. What is really nice is that here I just used data set that was publicly available. You didn't have to annotate anything by hand. I didn't have this kind of images. I just had fluorescence images. And by just doing the stain deconvolution and combining them, I'm able to get very nice results. So it's not perfect, but really for the time I spent doing that, it's quite amazing. So now maybe I could play on the threshold a bit more. Kind of question you want to ask is this real? So here I don't have anything. Should I have something? I don't know, because I'm not very familiar with these images. Here, maybe I want to segment these guys, and I guess I need to decrease. But again, are there real nuclei, or are they just so different kind of cells that are very small nuclei? It's possible. In that case, I probably want to get them. Or is it just because they are not in the plane? It's we are looking at a 2D image, but these objects are 3D, and we just have one part of them, and it's it's the main part of the nucleus is missing, and it explains why I don't get them. That's the kind of question we need to ask. I think here we are doing quite a good job. So so I'm gonna use these parameters, not saying that these are the best parameters, but I'm gonna use these parameters. And I'm gonna run it for the entire annotation, which might take some time. So I'm gonna delete this annotation, delete the descendant object, and select this and run it. So it's gonna take a little bit of time. So I'm gonna start the running, and I'm gonna just speed up the video so you don't have to wait for the entire processing time. All right, it's down. So it took quite some time, about 2 hours. So quite some more time than with the watershed, but could be improved by using a GPU implementation of QuPath. So if I close this, this is what we got. So it looks okay. So I tried to also obtain the small nuclei, and so maybe it wasn't that good idea. Here it works fine, but in that case I also get things. The background here, this is clearly dust and not a nucleus. And by using a filtering out the nuclei that are small, I could have removed this one. But overall, it looks really nice. So now the next step is to actually identify the positive cells for DAB. And so here we could do an object classifier. We could train an object classifier. In that case, I'm gonna instead use a thresholding. So it's gonna be very similar to what we did when we used the positive cell detection. But it's just a bit different. So it's called create single measurement classifier. And it looks like this. So in that case, you can use a subset of the detections or all detections. You can filter them out. So this is fine. You define the measurement you want to use. So it can be a measurement based on morphology. If you want to, for example, if you were to try to identify lymphocytes, we know that their nucleus is smaller, so using the size could be a good idea. The area of a nucleus here. Here we want to identify the DAB positive cells, so we're going to look at the DAB, and as before, the average intensity in the nucleus is going to be it's probably going to be a good idea. I'm going to use DAB nucleus mean. So it is a threshold, and then we're going to classify all the nuclei that have an average intensity in the nucleus that is superior to a given threshold as being part of a class. So above, you can do it for above threshold and below threshold. Here, only above threshold is interesting for us, but I need to actually define a new class. I'm going to called dab. So here, I'm going to do add class. I'm going to call it dab plus for dab positive. And so everything that is above the threshold is going to be dab positive. And you can do interactively. So again, I can just look at the nuclei because it is nuclei. So if I do a live preview, then so you see it's not great because of the color. Dab is in purple. I can try to change it to have something that is more different than purple from red. So let's, for example, lime is really different. Yeah, makes things easier here. And so so then you can change thresholds. Obviously, if I put something high, I'm gonna get less positive, and here I'm missing this guy. So obviously it's too high. If I put something really low, I'm gonna probably consider things that are not positive, I guess. Now you can look at the histogram of DAB, and clearly there's a huge peak corresponding to cells that are not that positive, and probably something around 0.5. It's probably too high. Here, I guess 0. Yeah, because this is clearly positive. So you can select cells, and that might be useful because here I can look at the DAB average intensity of DAB in the nucleus here, and it's 0.48. So it's almost positive. I can maybe try to find nuclei that are more borderline, like this one. So it's still 49. This guy is 42. So maybe 0.4 is going to be good enough. So then you can obviously you can check, you can move completely different areas, and you can check. So again, segmentation looks pretty nice. I guess this is probably positive, and it's 0.34. So I'm gonna decrease it to 0.3. So now, sorry, I zoomed out. Now you have this kind of examples where you don't really know. That is 0.31, but I guess, oops, it's not what I wanted to do, sorry. Not a good example. I wanted to look at, yeah, so here, for example, it might look, borderline, but still seems to get some depth. So what I wanted to do before is that, looking at the hematoxylin, here, I've barely anything, and so it's definitely depth. So I think that makes sense to have this cell defined as depth positive. I'm going to go back to this, and so you can, you define the threshold that makes sense for your study, and when you're happy with it, you can just apply it. And now, so I didn't save it. Yeah, that was maybe not the best way, so it depends. If you just do it for your image, it's fine. If you want to then apply the same classifier, you can save it, and then you can load it to apply it again. And the way to load the classifier is the same way to load an object classifier, and this will do it with fluorescence. So you'll see how to do it. Now, if you want to look at the measurements, you can go into, so if you go to show detection measurements here, you have again one line per cell with all the measurements associated with the cells we just saw, and you can see if it's nothing, negative, or that positive. What might be more interesting if you just want to have the proportion of cells you have here, you can just go to show annotation measurements. And in that case, you'll have only one line because we only have one annotation with like this. And you have what's going to be interesting here is the total number of detection. So here it's something like 1,502,000. And the number of DAP positive, which is 267,94. It's about a fifth, a little bit less than a fifth, so we are between 15% and 20%. So it's interesting because it's pretty close to what we had with the watershed, actually.